For this section, we're going to look at factoring special forms, or you can sometimes think of this as special products. We talked about special products when we were talking about polynomials. So as a kind of a reminder, in math, special products refer to special patterns or formulas used to simplify the multiplication of algebraic expressions, especially polynomials. These patterns help you expand or factor expressions without having to work through each term manually. So basically, we have special patterns that if we can recognize a pattern, it factors a certain way. So it multiplies to have a certain pattern and it factors backwards to have a certain pattern, okay? So if we can learn these patterns, we can save ourselves a lot of time, okay? So the first special product that we want to look at is the difference of perfect squares, okay? So basically, back when we were talking, back when we were talking about, I don't know what I'm doing. Back when we were talking about polynomials, we had conjugate pairs. So conjugate pairs were something like a plus b times a minus b. We had the same terms, but we added in one binomial and we subtracted in another, and they multiplied beautifully. So we found that if we had something like x plus 5 times x minus 5, well, we would FOIL and get x squared, x times negative 5, 5 times x, and then 5 times negative 5. And what happened was those middle terms always canceled out to just become 0. So anytime you multiply conjugate pairs, things cancel out and just become a 0 in the middle. So we would be left with x squared minus 25. Well, the result is the difference, so subtraction, of perfect squares. So now we're going to look at this idea of the difference of perfect squares. We're going to start with that difference, and we're going to find out how can we factor that backwards to where we get conjugate pair binomial answers or binomial factors. Okay, so let's talk about a couple of things before we dive into the factoring. First, just in case you have forgotten, the square root of a number is one of two identical factors of that number. So if we think of the square root of 25, it equals 5 because 5 times 5, two identical factors equal 25. Whoops, I'm kind of blending my notes here. Okay, so the square root is one of those two identical factors. Now, a perfect square is a number with an integer square root. 25 would be considered a perfect square because the square root of it's a nice, pretty whole number answer. Okay, now, as far as variables are concerned, you know a variable is a perfect square if it has an even exponent. So exponents of 2, 4, 6, 8, 10, whatever, those are perfect squares, okay? And the way you find the square root is you keep the variable and then you just divide the exponent by 2, and that's the square root, okay? So let's talk about the difference of perfect squares. So the form or the pattern that we need to recognize is that if a and b are real numbers, okay, variables or expressions, so a and b can be just numbers, they could be variables, they could be expressions, then you would have something like this. A squared represents a perfect square, b squared represents a perfect square, and if we take the square root of a squared and the square root of b squared, we just get a and b. And so that tells us that as long as you have the difference of perfect squares, difference being subtraction, you can take the square root of those two terms, add the square roots, subtract the square roots, and there's your conjugate pairs. So you just have to make sure you have two terms. You can't have more than two terms. So this is just the difference of two perfect squares. So you have to have two terms. You have to be subtracting those two terms, and those two terms have to be perfect squares. If those patterns or those features are met, then you take the square root of those two terms, add the square roots, subtract the square roots, and that's it. Okay? So for example one, let's do 4 examples. So example 1 has 4 parts. Ooh, I do need to mention this. One thing you do need to notice is the sum of squares is prime. This is exclusive to the difference of squares, which means subtract, okay? So if you have two perfect squares, but you're adding them, no luck. Nothing's going to happen there, okay? You could potentially have a GCF, but that's it. All right, so factor each polynomial completely. Let's look at the square root of x squared first. Well, we have an even exponent, so we know that x squared is a perfect square. The square root of that would just be that variable with the exponent divided by 2. Well, 2 divided by 2 is just 1, so we would get x to the first or just x. We also need to look at the square root of 144. Well, it just so happens 144 is a perfect square. Most of us kind of remember 144, but if not, you can always go to your calculator. And where do I have my calculator? Here. So we go to the calculator, and if you have a graphing calculator like this, you want to look for the square root symbol, which on this calculator, I have the x squared button. And if you notice in blue in the corner, I have a little square root symbol, which we technically call a radical symbol. We'll learn more about that later. But I would hit the second button and then the x squared button, and then you type in what's called your radicand. That's the stuff under the square root. And then hit enter, and we get that this is 12. So the square root of 144 is 12. Since it's a nice, pretty number, that tells us that we do have a perfect square. So the square root here is 12. So we've met the criteria. We have two terms. We're subtracting. Both terms are perfect squares. So we just factor by taking those square roots, adding them, and then subtracting them. And notice the final result, conjugate pairs, okay? And if you want to check this, you can check these by foiling, just like you did in the previous worksheets. So if you want to check, we would take x plus 12 times x minus 12. Now, technically, this is, one of those special products, so we can kind of do a shortcut here, but just for the sake of making sure we understand that this works, let's FOIL this out like longhand. So x times x is x squared. X times negative 12 is negative 12x. 12 times x is positive 12x. And 12 times negative 12 is negative 144. Notice those middle terms are opposites. If I take negative 12x and I add 12x, I just get 0. So I get x squared minus 144, which is exactly what we started with. Okay, so this works. Now, if we go to part B is a teeny bit tricky. I would encourage you, no matter what, to always look to see if you have a GCF, okay? Always. It's going to save you time in the end. Now, if we look at part B, 4 is a perfect square. Its square root is 2. 100 is a perfect square. Its square root is 10. X squared is a perfect square. Its square root is x. But look for a GCF, because at the end of the day, we need to make sure we have factored completely. That means our final answer has no common factors or GCFs or anything that can be divided out. And the way to save yourself a little bit of heartache is look to see if you have a GCF first. And in this case, we do. So we have a GCF of 4. So let's go ahead and take care of that GCF first. So I'm going to divide out a 4. Well, 4x squared divided by 4 is just x squared. 100 or negative 100 divided by 4 is just negative 25. Well, notice we still have the difference of perfect squares. The square root of x squared is x. The square root of 25 is 5. So we still meet the criteria for the difference of perfect squares. So I want to keep the 4 that I originally factored out. And then I want to take those square roots that I found, and I want to add them and then subtract them. And there you have it. So if you wanted to check this one, you could multiply the two binomials and then distribute a 4 at the end. Okay? So there you have it. Factoring the difference of squares is quick. It's easy. All right. X squared, or no, x to the 4th minus 16. So let's look at the square root of x to the 4th. Well, that's just going to be x, and then to the 4 divided by 2. Well, 4 divided by 2 is 2, so we just get x squared. Square root of 16 is 4. So we've met the criteria. Our first and last term, or I guess both of our terms, are perfect squares. We have exactly 2 terms. We're subtracting. We've met all the criteria to be the difference of squares. So we would just say this is x squared plus 4, x squared minus 4. And then stop and take a breath and look at your answer and shout out to wherever you're at, your bedroom, your living room, wherever. What do you notice about that second binomial? Hopefully you're all like, it's the difference of perfect squares. So if you look at the first binomial, we have x squared plus 4. Well, we're adding, it doesn't fit the criteria right off the bat to be the difference of squares. But if you look at the second binomial, we have exactly 2 terms. We're subtracting, and both terms are perfect squares. So we can factor again, okay? So if we look at the square root of x squared, it's x. The square root of 4 is 2. So I'm just going to bring down my x squared plus 4. Think of it, it's not a GCF, but think of it as almost like that GCF that you have to carry through your problem. That first factor of x squared plus 4, bring it down. And then the x squared minus 4, we can factor. It's the difference of squares all on its own, so we take the sum of its square roots, x plus 2, and then the difference of its square roots. And that's it. So there you have it. So if you wanted to check this one, you'd probably, I would say, multiply the second two binomials, and then when you're done with that, FOIL that with the x squared plus 4. Okay? Now, last up, let's see, we have 9x squared minus 64y squared. We do not have a GCF here, but we do have two terms, okay? We are subtracting, and everything is a perfect square. 9 is a perfect square, 64 is a perfect square, x squared is a perfect square, y squared is a perfect square. So we have difference of perfect squares here. So let's look at the square roots of each term. So 9x squared, the square root has two parts. We want to look at the square root of 9, which is 3. And then the square root of x squared is just x. Remember, if you have an even exponent, it's a perfect square. You keep the variable and then just divide the exponent by 2. 2 divided by 2 is 1, so we just get 3x. And then we need the square root of 64y squared. So again, two parts. The square root of 64, if you're unfamiliar with that, certainly use a calculator, but it is 8. And then y squared has an even exponent, so we keep the y and then just divide the exponent by 2. 2 divided by 2 is 1, so we get 8y. So our final answer here would be 3x plus 8y times 3x minus 8y. And you could certainly check this using your special product form from our chapter in polynomials, or if you wanted to, you could just flat out FOIL this out, okay? So that's the first example of a special product. Again, you have to make sure you meet the criteria. You have to have exactly two terms. You have to be subtracting those two terms. Both terms must be perfect squares for this to work. But knowing this shortcut, it's a pretty big time saver.